Okay, in the previous class, we studied about the purpose of RNN and the important aspects of RNN. A quick review of what we discussed in the last class. So, RNN is used for sequential data or sequence data, where the outcome depends on the previous outcomes, the present outcome. The output at time t depends on a function of the previous outputs t minus 1 and t minus 2, t minus 3, so on. So this is sequence data. So we discussed that CNN is very suitable for the image data, grid-like structure data, whereas RNN is suitable for more for sequential data. And RNN handles this data by feedback connection from the previous outputs. And we can also say that RNN has a memory. That means it has a channel to remember the previous outputs. Remember previous output to compute present output. So this is the main feature of RNN. It has a memory. So let us see the structure of RNN and how we can use this to understand the functioning of RNN. So RNN can be represented as a sequence of units. Let us say this is one unit and this is. So at time is equal to 0, you will be processing one. For example, we are dealing with a sentiment analysis problem where we have an input like let us say good, best. Let us say this is our input. So at time t is equal to 1, we will be sending this word. Time t is equal to 2, we will be sending this word. Time t is equal to 3, we will be sending this word. So when we send this word, we call this as x11, and this is x12, and this is x13. Now what is happening here? I'm sending x11. I'm sending x11, and here at time 2, I'm sending x12, and here at time 3, I'm sending x13, and if there is if I can send x14. So this is the input, x is the input term. Apart from that, we have a weight matrix U. So we can call this Wi or U. U is the weight matrix from input to the hidden. Now this is the hidden layer. And let us say, and from here, the output is coming as O1. And here the output is O2. And here the output is O3. And here the output is O4. Later, based on all these four, you may calculate Y cap. And this output 1, to calculate Y cap, you may have weight vector V, and this also weight vector V, this also weight vector V, this also weight vector V. So what else we have? When time t is equal to 1, the O1 is calculated as, if the activation function is tan h, then the weight matrix U into X11 plus that particular bias, let us call it as BI or whatever it is, BI input unit or hidden unit bias, plus not only this term, but we are getting at time 2, we are getting an output here, whatever you are calculating here. And time 2, you are getting an output O2. That is fed into this one. So when you are calculating O2, O2 is tan h of U X12 plus that particular bias B2 plus what else? You are also sending O1 and we call that matrix as W, weight matrix of the hidden to hidden is O1. So W O1. That means to calculate O2, you are using O1. And similarly, what is O3? O3 is tan H UX13 plus D3, that particular bias, plus WO2. So to standardize it, we'll say some random number or something O0. So O1 is calculated as O0 into W. Same weights are used. And obviously, once you calculate O, we'll be calculating Y cap, Y1 cap by, if you are using sigmoid function there, then the weight matrix is V into the O1, the weights, plus that particular bias, BO, or that's it. Similarly, you can calculate Y1, Y2 cap and Y3 cap, and you will calculate Y cap if it is required. So this, what we called it as forward propagation, and we can, this is unfolding of a single tree-like structure where we have U and this is XP, and here we have O1, and from this you are calculating Y cap, and this O1 is again fed here as the input. So this is the unfolding of this particular graph. Now let us see what we do with back propagation, how the back propagation occurs. We already know in the previous classes what is the back propagation and how it works, that we have seen. So what actually happens in back propagation? And here remember, we are just not calling it back propagation, but we are calling it a special term, back propagation through time. We indicate it by BPTT, back propagation through time. So what actually is back propagation? We have three weights, U, weight vector from input to hidden, then we have weight vector V, weight vector from hidden to output, and we have weight vector W, weight vector from hidden to hidden. So first we initialize these weight vectors to some random variables or zeros, and based on these weight vectors, just now we have calculated O1 and Y1 cap. So we'll be calculating overall Y cap. What is Y cap? This is the computed output or predicted output. Predicted output. Once we calculate the predicted output, what we do, we also calculate, we also know the actual output. We also know the actual output. What is the actual output? Y. Sorry, it's Y. Actual output. So based on these two, the difference between the actual value and that predicted value, we call that as a loss function or cost function. I already told you in the previous classes that whenever you take an example and calculate local difference, we call that as a loss. When you calculate it for all the examples, we call that as cost function. So it is either loss function or cost function. We indicate it by E, or some textbooks they indicate it by loss L. So as machine learning or deep learning engineers, our attempt, our objective is to minimize this loss, minimize the deviation from the actual output. We want our model to predict Y cap as close as possible to the Y. And what is our task here? We want to find set of weights. What are weights here? We are having three sets of weights, U, V, W, such that the loss or the error is very minimum, if not zero. This is our attempt in all our algorithms. Mathematically speaking, we want the gradient. What is gradient? The change in the error, the change in error when we change particular weight. This we want to be, this error is important to us. So do we want this gradient E to be small or zero? We want to find the weights when this is zero. That particular weight we want. So weight at which our task is to find weights at which the gradient is minimum. This is our task. So I want to find U, V, W such that I want to find U such that dou U by dou W, sorry, dou E by dou U is zero or minimum. Similarly, I want to find V such that Dou E by dou V is minimum. Similarly, dou E by dou W is minimum. So we want our gradient change in error with respect to change to be as minimum as possible. This is our task.